So, good evening, everyone, and I welcome you all to today's live session. We are in the week 4 live session for the course Nonlinear Vibration NOC25 ME57, and this course is being taught by Professor S.K. Dwivedi of IIT Guwahati, and I'm Rashia Didi Ranjan, NPTEL PMRFTA in the Department of Mechanical Engineering, IIT Patna. And already we have done 4 weeks into the live session and we have talked about how do we deal with the nonlinear system, how do we identify the nonlinear system, how numerically we can solve it, how analytically we can solve to get the approximate analytical solution, and etc. Okay, so coming on to the overview of this week. So this week was analytically less exhausting, I would say, because the previous 2 weeks were very analytically exhausting. We had many things that we had to do, that too analytically. Okay. So this week we again got into a bit of a concept that what could be the probable response of a nonlinear system, wherein we again discussed that the response may be a fixed point, could be a fixed point, it could be periodic, could be quasi-periodic, or it could be chaotic. Okay, and we have already been discussing about what is a fixed point response, what is a periodic response, what is a quasi-periodic response, and what is a chaotic response. What are the, like, I would say, properties of chaotic response, and how to identify a chaotic response and everything. Okay, and now then in this week's classes, the phase plot for a system was discussed. Like basically, it was discussed that if we want to show that how do we plot the behavior of a system. Like for example, I know the equation of my system, right? And I want to, visually represent how my system is behaving with time and what are its properties. Excuse me for a second. Yes, so if I would like to talk about that, how would I represent my system visually? So there were three things essentially: time response, phase plot, and Poincare section. So time response, when we plot the response with respect to time. Phase plot is nothing but the plot of the displacement versus velocity. Poincare section, I'll not define as of now. We will actually deal with it in the further lectures and we would discuss it at that time only. But what I could tell is that Poincare section is very important to visually differentiate between a periodic, quasi-periodic, or a chaotic response. Okay. Then the discussions were also done for the jump up and jump down phenomena, which essentially occurs in physical systems, specifically those systems which have linearity present in them. And I've also taken a question in which I will discuss about this jump up and jump down phenomena. Then stability analysis was taken up in this week's lecture, wherein how can we actually work on the stability to find out the stability of the fixed point of the system could be done was discussed, and the last lecture was basically concentrated on the numerical techniques, right? And it introduced the different kind of numerical techniques that could be used for differentiation, integration, and for finding the roots. Like for example, for differentiation, we know that, like for example, if I know y as a function of x, and if I want to find dy by dx, what I could possibly do is that I could fragment my x into different segments, right? I would cut out my domain into small pieces of x, and I can write dy by dx as nothing but f of x plus h minus f of x divided by x plus h minus h. and this would give me the value of differentiation. So this is essentially used for numerical differentiation, right? Like for example, if I know this, and if it's a continuous function, if f is a continuous function, I can simply differentiate this, right? And get the function, a continuous form of the differentiation, right? But what if fx is discontinuous? It is very difficult for me to differentiate. In that case, what I can do is I can calculate the numerical differentiation. Yes, definitely it converts my continuous system into a discrete system. Similarly, I could perform the integration, which we have already done using the ODE45, right? We were using the ODE45, RK4 method, or Euler method, any one which you can use in order to perform the integration, numerical integration. And the third one is for finding the roots. Like, for example, we have the bisection method in which we uh, like do the sum of, like, for example, if I have a function like this, and this is the axis, and this is 0, so we know that between this and this there should be a root, but I don't know the value. So what I can do is I can just take the average of this, which would somewhere be here, and I can see what is the value, whether it is positive or whether it is negative. So I get that, okay, this is positive, so then I can take the average of these both, and then I can get this value. Likewise, this iteration will go on till I reach this point, which is the root, right? So this is the numerical way of finding the root. See, if you have a simple equation, then you can find the root by simply by calculating it on your own, right? Now, if you have a algebraic equation of very higher power, then also you can use MATLAB to find the roots. But what if you have transcendental functions like sine x, cos x, log x, e to the power x, along with the algebraic terms, then you have the negative powers and everything all stacked up in the same equation, then what would you do? See, it becomes very difficult to find the roots by doing the analytical formulation, or even uh, giving MATLAB to solve it. So in that case, we use the numerical technique to find the root of the equation. Okay. So this is what was discussed in this whole week, and I hope you people are clear about all these things. Okay. Along with the bisection method, there were also other methods like the regular falsi method, etc., etc. Okay. All of the things were taught nicely in the lectures. Okay, we'll just jump up into the questions. Okay, so the question says, which of the following system has strong nonlinearity? So why is there a difference between strong and weak nonlinearity? And how is it even important that we should know that whether my system is having a strong or weak nonlinearity, right? So the thing is that, if my system is having linearity and then there is a nonlinear term. Okay, so I want to find the solution. So there are two approaches we know. One is the numerical method, second one is the analytical method. However, how would I know which method I should go with? See, the analytical method is definitely the advantageous one because I get a closed form solution, right? And then that closed form solution I can use further for my application purpose, right? And it is better for me. If I go into the numerical solution, though the numerical solution can probably give me the exact solution, but it comes with a probability, right? Because if I solve it through a numerical method, I have to Because when I solve it through the numerical method, what do I have to do? I have to actually consider the equation. I have to consider which kind of a numerical method I should apply. Like it should be the implicit method, it should be the explicit method, or it should be a combination of the implicit and explicit method. I have to find out about the stiffness of the nonlinear equation. I have to find out that what amount of step size I should be taking, right? So that I could get a better solution or the exact solution, right? So that is why it is important that I know. So see, if I have a strong nonlinearity, now I know that okay, if it is having a strong nonlinearity, so I should go with the numerical solution. Because if you remember, when we were talking about the analytical methods, we were assuming that our equations or the nonlinearity are multiplied with the bookkeeping parameter epsilon, correct? Multiplied with a bookkeeping parameter epsilon, right? all the nonlinearities so that it goes into the second equation or the maybe the third equation and not the first equation. So if it is getting multiplied by epsilon, it means that its value is small, right? Because epsilon's value is smaller than 1. So it should be smaller than 1, which means that its effect is not that much as compared to the other terms of the equation. Or should I say the coefficients of the linear terms? Right. So in that case, what I can do, I can go with the analytical solution because I would get a approximate solution that is good to go. Right. But what if I have a very high value of the coefficient, or I should say it is comparable to the other coefficients of the linear term? In that case, I should go with the numerical solution. Right. This is the analogy that one follows. So that is fine. Okay. If I have strong nonlinearity, I'll go with the numerical technique. If I have weak nonlinearity, I can go with the approximate analytical solution. That's fine. But how to identify it? How would I know just by merely seeing the equation whether my system is having strong nonlinearity or weak nonlinearity? Right? Whether it is having strong forcing, whether it is having weak forcing. Correct. So it is essentially, I would say, let that how do we actually identify it? So let us assume, let for the Duffing equation, let us assume it as this plus, okay, let us assume this Duffing equation, okay. Now for this Duffing equation, if my f, if my value of f is comparable with the value of omega n square, if my value of f is comparable with the value of omega n square, then I would say that my system has a strong forcing, right? And if my value of f is very small as compared to the value of omega n square, in that case, what would I say? In that case, I would say that my system is having a weak forcing. Very simple, right? So if f is comparable, now when I say comparable, I mean that if omega n square is 1, f could be 0.9, f could be 1.1, it could be 0.8, 1.3, something like that. Okay, okay, so this is what it is. Okay, so the value of f, it is comparable, we say that it has strong forcing. If it is less, we say that it has weak forcing. But okay, so it should be something like that f could be written as this. Okay, could be written as this. So if it is multiplied by epsilon, which is the bookkeeping parameter, definitely it has a less effect as compared to the x. Okay, now this was for forcing, strong forcing, weak forcing. But the question says about strong nonlinearity or weak nonlinearity, right? Analogous to this, we would talk about the nonlinearity, right? So if the coefficient of the nonlinear term is greater, than that of the coefficient of the x term, then we would say that the system has strong nonlinearity. However, if it is small, then we would say that the system has a weak nonlinearity, right? However, it is worth mentioning that these terms are highly relatable, you know. Like for example, if I'm comparing two Duffing equations with each other, then only I can say that any of the two is having strong nonlinearity or weak nonlinearity, right? I cannot take a Duffing equation and just compare it with the Van der Pol equation. That is not correct way of comparing. Okay, so that is why I'm saying that this strong nonlinearity and weak nonlinearity is a highly relatable term. It should be used only for relating 3-4 equations, which is of a similar type, right? You cannot compare two very different equations and give a conclusion that any of the two system is strongly nonlinear or weakly nonlinear. Okay, this should be always be kept in mind. Okay, so coming on to the options that has been given. So if we see the first option, we have omega n square as 1, and the nonlinear term is having a coefficient of 0.1, right? So 0.1 is definitely very less than 1. And we can consider 0.1 as the bookkeeping parameter as well, because in some cases we consider the bookkeeping parameter as 0.1, right? So in that case, what we can do is we can say that this is not a strong nonlinearity kind of a equation or presence. Okay. Coming on to the second equation, here my omega n square is 2, right? And the nonlinear term has a coefficient of 0.01. Again, it is very much less than 2. So nothing could be said. Here my omega n square is 4. Okay. And I don't have any nonlinear term, right? So doesn't matter. And if I talk about this, here my omega n is what? 2. And the x cube term is 0.3. Correct? Now if I see, or I should I say, if I compare these three, right? If it would have been x square or x cube, then I would say that this is the correct answer, right? Right, but that is not true. So then what should be the correct answer, right? What should be the correct answer? So we will have to compare, right? Here I have 1 and 0.1. Here I have 2 and 0.01. Anyways, this is not going, B is not going to be the correct answer. So either A is going to be the correct answer or D is going to be the correct answer. Alright, so we have to compare under root 2, sorry, 2 with 0.3. Alright, so anyways, this is more as compared to the first option. So this would be the correct option here. But see, what I'm trying to say is, this is a comparable question. I have these 4 options, right? If I would have any other option, then that would be correct, right? This term, if I look at this equation, just as at this equation, if I look, I would never say that it is having a strong nonlinearity, right? Because 0.3 is very small as compared to 2, right? But since I have to choose between the 4, among these 4, which has the strong nonlinearity, right? So the option D is correct. But if I have only option D, then I would write no, this does not have a strong nonlinearity. Okay, so that is why I said that this is essentially a comparable term when we talk about strong nonlinearity or strong or weak nonlinearity, right? However, in terms of forcing, it is different. You know why? Because in case of a forcing, whatever be the left hand side of the equation, the right hand side is always going to be the same. the right hand side is always going to be the same. It is always going to be of the form f cos omega t. It is always going to be of this form, right? However, if I talk about nonlinearity, here I have taken x cube, but there is x square. There could be x to the power 5. There could be x to the power 10, right? So, like for example, I could have 0.01 x to the power 10, right? And I could have, let us say this as 1. And I could have 0.1 x square, right? So, if now someone says that among this, which one is having a strong nonlinearity? So, see, though this has a coefficient greater than the above one. But what is important is to see that the x is at a 10th power. X is at the 10th power. However, in the below one, it is at the second power, right? 10th power will anyways supersede the square term. If my x is greater than 1, it is going to have a very significant effect, right? So that is why it is important that we always keep in mind that strong or weak nonlinearity should always be given on the basis of comparison with the similar kind of a equation. However, there is no such thing with the forcing term, because the forcing is always written in this form, right? I hope that this question is clear. We would go into the second question now. Okay. So I have taken this question in order to introduce the concept of sub and super harmonics, which is a very important concept in case of a nonlinear system. Okay, so what I will do is I will try to analytically show that where does this super harmonic or subharmonic occur? Why does this actually occur? Okay. So then once I will show it analytically, then I will tell you what is a super harmonic, what is a subharmonic, right? Okay, so let us consider the equation x double dot plus kx plus cx dot plus beta x square is equals to f cos omega t. Okay, f cos of omega t. Now, talking about what is this? So this is essentially a Duffing oscillator, right? With x square nonlinearity, and yeah, and it has a forcing function f cos omega t, right? Now, what is important here to note is that omega is the frequency of forcing, right? Omega is the frequency of forcing, whatever the forcing we have applied, right? And it is definitely different from the natural frequency, which would be under root of k. So let us assume, okay, I have assumed the solution as nothing but a naught cos of lambda t plus b naught sine of lambda t. What is lambda? Lambda is the frequency of oscillation, and we have till now assumed that my lambda is not equal to omega. Okay, if my lambda is equal to omega, now if you people remember, we have already done some questions on the harmonic balance method, and that is what we are going to apply over here. We have already assumed the solution, and what we are going to do, we will use this solution, the equation. We are going to use this, put it into the equation, and we will try to find out the relation between lambda and omega, right? And we'll see that what solution we are getting, right? If what if lambda is equal to omega? What if lambda is not equal to omega? So we will see that. Okay. Okay. So now as I have x of solution, I can find out x dot of solution, right? So this would be, okay, this is clear, I guess. Nothing, simple differentiation. X we already know. We want x square, x all square will be nothing but, okay, simple. A plus b whole square is equals to a square plus b square plus twice of ab. Okay, now what I will do, now since I have cos and sine terms, I have the freedom of applying the trigonometric relations that we all know, right? So if I take those trigonometric equations, first one is nothing but cos square x, 1 plus cos 2x by 2. Then we have sine square x is equals to 1 minus cos 2x by 2. And the third one is twice of sine of x cos of x is equals to, this is I guess sine of twice of x. Putting this in the previous equation, what do we get? We had a naught square cos square. Okay, we had a naught square by, yeah, a naught square into 1 plus cos 2x by 2. And then we have plus b naught square, 1 minus cos, sorry, it should not be x, it should be lambda t, lambda t by 2. And then we have nothing but, twice will be gone, a naught b naught sine of twice of lambda 2, right? Let me check. Okay, okay, yeah. So this is essentially my x solution square, right? Now since I have already got the equation, see, I have x double dot, I have x dot, I have x square, right? I already have these equations. I will put it in the main equation, right? I will put these in the main equation and then I can expand. So I will not do the whole process since we are not interested in finding out the proper solution. Rather, we are interested in knowing the concept of sub and super harmonics. So what is important is to see that if I relook to x naught, I have a term of sine of lambda t, I have cos lambda t. If I relook at x double dot of solution, I have cos of lambda t, I have sine of lambda t. Then if I relook at x square of solution, it is nothing but a naught square by 2, b naught square by 2 plus some terms of cos twice of lambda t and sine twice of lambda t, right? So what do I see? I can see that I can actually write the whole solution, like the whole equation when I put all these values in the main equation, whatever I'm going to get in the LHS, what am I going to do? I can write it in a generalized form, right? So after putting x sol dot in the main TE comma, the equation may be written generalized form as, see there are two constant terms, so we can write as a naught plus a1 cos of t lambda t plus a2 cos of twice of lambda t, right? Because I have twice of lambda t. If you remember, we did a problem, I guess in the last week's live session, where we did the same thing. I think we considered x cube, cubic nonlinearity, and then what we did was we ignored the higher harmonics while finding out the solution, if you remember. Yeah, we ignored the higher harmonics as of that time, but this time we consider the higher harmonics. So what are we getting? This plus b1 sine of lambda t plus b2 sine of twice of lambda t is equals to f cos of omega t, right? Now if you see, a naught is equals to 0, b1 is equals to 0, and b2 is equals to 0. Why? Because on the right hand side, I don't have any term of sine of lambda of omega t or anything. I don't have a sine term and I don't have a constant term also on the right hand side. Right, in harmonic balance, what do? We actually relate the coefficients of the sine and cos terms on the left hand side with the right hand side. Right, here you can see that we don't have any constant term. b1 is equals to 0, b2 is equals to 0. Now there is only two things left, a1 cos of lambda t and a2 cos twice of lambda t. Now there could be two possible ways, right? There could be two possible ways. One is when lambda, case 1, lambda is equals to omega, and there is a case 2 where twice of lambda is equals to omega. This solution I know. This solution I know, right? This is for a linear system. If I have a system, a linear spring mass dashpot system with a forcing frequency of omega, its solution is going to be what? Its solution is going to be nothing but sinusoidal along with a frequency equal to the frequency of forcing. This I know. So this is for the linear case. Okay, true. This is fine for me. This is the simple linear case, right? But where is this coming from? So if you see it clearly, this twice of lambda term was coming because of the x square term, which is essentially the nonlinear term of our equation, right? So here my lambda is going to be nothing but omega by 2, right? Okay, that's fine. What is important here to see is that for a certain kind of a forcing, it may happen that my solution could be of the same force, of the same frequency as that of the forcing frequency, right? But it could also happen that my frequency could also be equal to the half of the forcing frequency, correct? And it is also important to see that here, since I have considered my solution as this, this, right? I could also consider my solution as the summation, okay, as a truncated series. This is a truncated series. I can still consider it as an expanded Fourier series, truncated at maybe some other like harmonic, right? In that case, I can also get lambda is equals to omega by 3 or maybe omega by 4, omega by 5, etc., etc. Like in this case also, here I have considered x square. If I take x cube, here I am going to get omega by 3, right? Because in the this here I'm going to get cube, cos cube of lambda t, and if when I convert it into the cos of lambda t and cos thrice of lambda t term, I'm going to get cos thrice of lambda t, and when I will equate, I will get lambda is equals to omega by 3. Right? So this case is fine for me, but the introduction of this case led to the introduction of sub and super harmonics. Okay, so the concept says that when my frequency is an integral multiple, sorry, if my frequency of oscillation is the integral multiple or demultiplier, integral demultiplier, right? That time I am going to have some other harmonics other than the main harmonic. And those other harmonics were divided as subharmonic and superharmonic, right? So if I have, if lambda is equals to omega by 2, okay, if lambda is equals to omega, my time period is going to be 2 pi by omega. Let us call it as t naught. If my lambda is omega by 2, my time period is going to be what? 2 pi by, which is going to be 4 pi by omega, which is nothing but twice of t naught, right? So if this is the case, then I call it as a sub, okay, no, super harmonic. I call it as a super harmonic. And if there is some other case where I have n omega, I call it as a subharmonic. Okay. So see, what we can see is that just the introduction of x square can actually lead to a solution which is going to have the frequency half to that of the forcing frequency, right? It sounds very absurd, right? That, but because when we learn in what we learn in mechanical vibration, it's like if I have damping in the system and if I have a forcing frequency, definitely the solution or the oscillation is always going to have a frequency equal to the forcing frequency, right? But in case of a nonlinear system, that is not true. It may lead to a kind of a oscillation where my forcing frequency could be omega by 2, it could be omega by 3, it could be twice of omega, thrice of omega, anything of that sort, right? So now the question says that the subharmonic of the frequency 30 hertz is, answer is going to be nothing but C. Okay, I hope this is clear. Okay, now coming on to question number 3. This question I have taken just to introduce the concept of trace and determinant, and this is essentially used in case of a matrix. Okay, we define the trace and determinant in case of a matrix. So if I have a matrix A, for a matrix 2 cross 2 matrix A, is equals to A11, A12, A21, A22. Okay, determinant is given as nothing but A11, A22 minus A21, A12. And trace is given as nothing but summation of the diagonal elements. Trace is nothing but the sum of the diagonal elements, which here is going to be A11 plus A22. Now this is for a matrix, but I have two differential equations. How will I find the trace and determinant? So, we can always convert n set of first order differential equation as a matrix, like in a matrix form. Okay, and then I can represent it in the form of a matrix in a single equation, right? That is what we do in quantum mechanics. Like, we don't have to then write three equations for the three dimensions. It becomes very difficult. Then we have the relative dimensions and everything, right? So that time we write it in a matrix form. So if I want to write this in matrix form, how can I write? See, I have x dot and then I have y dot, right? So I can write it as like this, and then I can write, okay, and then I can relate this as A is nothing but a transformation matrix, right? When you multiply these two vectors or these two matrix, you are going to get nothing but the same equation. Okay, but now I can write it as a single equation and it becomes easier for me to express this. Okay, so now I have A, right? A is nothing but 1, 1, 4 and minus 2. This is what I have. Now I have to do nothing. I have to find the trace and determinant. So determinant is nothing but 1 into minus 2 minus 4 into 1 minus 2 minus 4 minus 6, and then trace of A is nothing but 1 in, sorry, this is trace. We have to just sum up the diagonal elements. This is nothing but minus 1. Okay, so these are the trace and the determinant. Okay, okay. Now coming on to why was this question important? So that I will tell as the question will proceed, that how the trace and determinant actually are actually going to help me, in finding out the uh, solution, right? Because you know that this can be also used for determining the stability of a linear system. First, let us do those questions, then we will talk about it, right? Here only I will explain you. See, I have a equation, a second order differential equation, right? Now, for this second order differential equation, I want to know about its stability, right? How will I know about its stability? Okay, so we will have to use some analytical ways, right? So there is a concept, that says that for a two-dimensional system, like for example, if I talk about a single system, like if I have dy by dx as a function of x, right? What I can do, I can simply find out the solution by integrating. What I will do, I will write dy integration will be equal to f of x dx integration. That way I can get y as a function of x plus some constant. Let us say this as g, some constant. And by merely looking at this equation, we can tell uh, what is the stability, or even if not looking at the equation, we can plot it, we can use the numerical methods to vary the value of x and get the value of y, and then we can tell about, how the system is going to behave, right? I hope this is very easy to understand. Okay, this is fine for a single dimension system. But what about a two-dimensional system? I mean, for a two-dimensional system, we have a coupled equation, right? We have coupled equation. So for that coupled equation, how am I supposed to, relate? How am I supposed to solve it, right? So, for a two-dimensional system, when we talk about a two-dimensional system, we say that if we know two solutions, there could probably be two possible solutions, right? There could be many solutions, depending upon the initial condition, depending upon the parameter value, right? Let us just take the initial condition. So depending upon what initial condition I am giving, there could be many possible ways of getting of possible solutions, right? So if there could be many possible solutions, how can I get all those possible solutions? So the concept says that for a two-dimensional system, if I have two solutions, if I have two solutions, then I can find out the other solutions as a linear combination of those two solutions. The independent and dependent concept of dependent and independent vectors in space. This essentially comes in engineering mathematics, where we talk about dependent and independent vectors. And we say that for a space, if I know the independent vectors, okay, then I can find out all the dependent vectors by just the merely the linear combination of those independent vectors, right? So okay, let us just take the example of a Cartesian coordinate. XY coordinate, let us consider, right? In the vector space, if we say. So if we have a XY coordinate, right, in the vector space, and there is this point, which is as at a distance 5 from here and 3 from here, right? Now I want to specify you that, okay, currently this particular person is standing at this particular place, right? How will I tell you? How will I tell you? One way is I can tell you, okay, you start at the origin, go 5 kilometers in the x direction, go 3 kilometers in the y direction, and then you are going to reach at the point A, right? But we are engineers. We specify the point A as nothing but 5i plus 3j, right? Position vector. We know the concept of position vector, and we can write R in the vector form as 5i plus 3j. Now what is I and j over here? I cap and j cap. I cap and j cap are nothing but the unit vectors in the x coordinate and the y coordinate, x axis, y axis. Now if you see, if I talk about the vector space of x and y, this I is nothing but a unit vector in the this I vector is nothing but a unit vector in the x direction, and it is independent of the y direction. Correct? It is independent. And this j cap is nothing but the unit vector in the y direction independent of x. And since I know I cap and j cap, okay, since I know I cap and j cap, now I can write any vector or any position in the x and y coordinate by the help of these I cap and j cap, nothing but as a linear combination of I cap and j cap. Correct? So this is the concept, and we are going to apply it in a two-dimensional system. Now we know that this is a second order differential equation, right? For a second order differential equation, if I convert it into two first order differential equations, it becomes a two-dimensional system problem. See, though there is x position and x dot velocity, but those are two acceleration and velocity could be considered as a two dimension. I am not saying that in the coordinate it is going to be x and x dot, but we can consider as a two generalized coordinates, right? You know, there is difference between physical coordinate and a generalized coordinate, which I have already discussed, right? So that way, for a two-dimensional system, if I find out two solutions, then I could probably get all the solutions as the linear combination of those two solutions. Now the question is how to find the two solutions. How will I find the two solutions? How is it possible for me? So then there comes a concept, okay? Then there comes a concept of eigenvalue and eigenvector. If you know that the eigenvalue and eigenvector, how is it even important? So if I have a system given in the form this, which is equal to, right? So if my a of x is equal to lambda of x is a vector, right? This case, lambda is nothing but the eigenvalue and x is nothing but the eigenvector. So essentially, if I have my eigenvector or the eigendirection, what I can probably see is that in case of my eigendirection, you know, my x dot could be related to my x as just a multiplication with a value lambda. Remember, eigenvector is a scalar valued matrix. It is not a vector. It has a scalar value. So essentially, my x is multiplied with a scalar value, and then it gives x dot. Right? X is multiplied with a scalar value, and it gives x dot. So what does it bring to my mind? If I have x dot as nothing but some lambda into x, you know, I can get its solution. Why? Because then I have dx by dt is equals to lambda x. So I have dx by x is equals to lambda dt, and I can integrate it and get the solution as nothing but e to the power lambda t plus some constant. So now if I can convert my two-dimensional system in this form, then what I can do, I can write my solution, right? I will get the two solutions for a two-dimensional system. This matrix is going to be, you know, it is going to have two values, two variables. For those two variables, I can get two eigenvalues, right? For those two eigenvalues, what I can do, I can get the two solutions of this form, and I can make a linear combination of these two solutions, and that would give me the general solution. So this becomes easy for me, right? So this is what the concept is applied. By the use of eigenvectors and eigenvalues, I can actually find the central solution. Apart from that, what is also important, or I would say what is rather interesting, is that these eigenvalues could actually tell me how the system behavior is. How the system behavior is. See, Firstly, uh, I have this form, which means what? If I try to plot it, if this is my x dot could be nothing but this lambda into x. Here lambda is less than 1 definitely. If my lambda is greater than 1, it could be a bigger vector. Okay, so I know this. This will help me to get the two solutions. I get the two solutions and then I can write the general solution as the linear combination of those two solutions. So if I talk about, if I get the eigenvalues lambda 1 and lambda 2, what could be the general solution? Nothing but C1 e to the power lambda 1t plus C2 e to the power lambda 2t. This is going to be the solution of x, right? Now, since this lambda 1 and lambda 2 could tell me that how the stability of the system is going to be, right? Because it is exponential. See, e to the power lambda, if lambda is positive, we are going to get a certain sort of solution. If lambda is negative, then we are going to get a certain type of solution, right? So that could happen, right? So here I will introduce the concept of trace and determinant. So let A is equals to general, just a general form. A could be anything. We have just considered it to be A, B, C, D, right? Now, if I want to find the eigenvalue, okay, what is it going to be? What would we do? What do we do? A minus lambda I, we find the determinant equal to 0, and that way we get the value of the eigenvalues. So we have, right? So we have nothing but correct. If I try to break it, okay. So if you look carefully, my trace of A is A plus D. Let us consider this as tau. And my determinant, which is delta, is nothing but AD minus CB. Right? What am I going to get? Lambda square minus going to be 0. Now from here, I can find out lambda, right? For a biquadratic equation, or for a quadratic equation. Minus B plus minus under root of B square minus 4 divided by 2. Correct? This is what it is. Now, depending upon the trace and the determinant, my value of lambda I'm going to get. Okay, I will just take a few seconds to make you understand that if lambda is positive, my solution is unstable. You know why? Because we have e to the power lambda t. As t will increase exponentially, it will increase. So it's an unstable solution. If my lambda is negative, it's a stable solution. Stable solution e to the power minus of some constant into t. So as t will increase, that negative value is going to increase, and hence the exponential function is going to show a decrement. So it's a stable solution. If my lambda is imaginary of the form a plus iota b, a minus iota b. So here I have a positive A negative. If A is positive, see iota B, I have one A0. Okay, so if you remember, if I have e to the power iota theta, I can write it as cos theta plus iota sine theta, right? I can write it as cos theta plus iota sine theta, which is nothing but a sinusoidal kind of a solution. Okay, so it will just oscillate, okay, for a constant amplitude and a constant frequency. It will oscillate. Definitely the frequency and amplitude, whatever it is, it will depend. Like for example, the amplitude, it will depend upon the initial condition. If it's a nonlinear system, the frequency would depend upon the initial condition. That is different, but it is going to have a periodic solution, right? But if I have A positive or negative, here it is going to be a periodic solution. And if I have A positive, you see A positive means that along with the periodic kind of a behavior, the amplitude is going to increase. It is going to diverge to infinity, plus or minus infinity. So it is what? It is a spiral out kind of a behavior. Spiral out, unstable. And this will be definitely spiral in, stable. Okay, this is fine. Now I have this equation. What I can do? I can plot a graph between what? So see, I have two elements over here. One is the trace and the other one is the determinant. So I will try to plot. Okay. Now, see. First, let us consider the case where the solution is a real number. For that, t square minus 4 delta should be equal to what? 0. So we are going to have a what? So if this is my trace and this is my delta, we are going to have a parabolic variation, right? So plotting a parabolic variation, something like this. Okay. So we have, okay. So now if t square minus 4 delta, if it is greater than what? 0, then we are going to have a either a stable solution or unstable solution. It would depend upon the value, but it is going to, the lambda is going to be a real number. All right. So for that, it to be a real number greater. So this is tau square minus 4 delta. So we have this one, this area, and then we have this area. Okay. Yeah. So here we are going to have a stable behavior, which means that it will drift back to the equilibrium or the fixed position, right? So in that case, what do we call? We call that my equilibrium point is a stable. We call that my equilibrium point is a stable center. It is a stable center. While for this area, my system is going to diverge, right? It is going to diverge. If you'll see, it will diverge. So here I am going to get a saddle node. No, actually we would not call it center because This terminology is fine. Stable node and saddle point. This is clear, right? Because see, tau here is positive, tau here is negative, right? So with a negative value, we are going to get a negative value of lambda. For negative value of lambda, yeah, for negative value of lambda, the system is going to come back to the equilibrium point. However, here we have the tau as positive, right? And our tau square minus 4 lambda is again, you can see here over here, it is positive. So it would what? It would lead us to the negative side, right? Negative side as in the system is going to go get unbounded. So it would lead to, there is spelling mistake, it would lead to nothing but the divergence of the system from the fixed point, and hence we call the fixed point as a saddle point. Okay, now coming on to, okay, this should not be called a saddle, actually this should be unstable. We will call this as saddle, why? Because the concept of saddle essentially comes from the presence of a point which is converging from a particular direction and diverging from a particular direction. While in case of unstable point, we have divergence in both the directions. Okay. So when there is the presence of a unstable point and a stable node, like for example, there is a point in a particular direction, it is coming to the fixed point. However, as soon as it tries to come the other direction, it is going to diverge it. That kind of a point is known as a saddle point, which we will see in this example only. We are going to have a saddle point. Okay, coming on to this, we will see tau square minus 4 lambda. Here we have, right? So we are now inside, which means that we are going to have a iota, we are going to have a like imaginary value with ourselves. Along with the imaginary value, our tau is going to be positive or it is going to be negative. So with the anyways, it is imaginary, so it is going to be a spiral behavior. With a positive tau, it is going to be a spiral out. With a negative tau, spiral in. Okay, that is how it is. Now coming on to this particular position, the lambda. Yeah, what is going to be with lambda over here? Here, if you can see, my tau is equal to 0. The trace is equal to 0. See, the trace is gone. So what do I have? I have nothing plus under root of minus 4 delta by 2. So there is essentially presence of two imaginary set of lambda which has 0 real part. How the behavior was there? How was the behavior when we had just the imaginary value with the real part 0? It was a periodic oscillation, right? There was oscillation. So this kind of a fixed point is known as the center. The fixed point which leads to the periodic behavior of a particular amplitude, right, is known as the center. Like for case of a spring mass system, it's a center, right? Because when we oscillate, we give a perturbation and then a system starts oscillating. Correct? So that is how it is, right? Coming back to our main question. I hope this was clear. This is given in many textbooks also, okay? And this was discussed in the lecture also. So I thought maybe I'll just give a brief about it. So we have this equation now. Now what? First we have to convert it into two equations, two first order differential equations. What will we do? We will have one, because we have two generalized coordinates x and x dot. So we have two equations, x dot and x double dot. This is equals to x and this is equals to, yeah, let us just call it like z, z dot of 1, z dot of 2, right? So now I have two equations, correct? Clear? I have hope there is no doubt. Now for these two equations, what will I do? Look at the question. What is the question asking? The question is saying that we have to draw the phase plot and comment on its stability. Alright. So for the phase plot, how will I draw the phase plot if I don't know the solution? So then I'll again apply the concept of finding the eigenvalues, eigenvectors, get the general solution, and then I can plot the phase plot. And once I plot the phase plot, I can simply tell about the stability of the fixed points. Right. So first I'll have to find the way in which I can relate it. So I have, like, I'm going to get the matrix A as nothing but 0, 1, 1, 0. Correct? This is going to be my A matrix, right? So now if I want to find out the eigenvalues, what will I do? A minus lambda I, determinant equal to 0. These are my eigenvalues. Lambda 1 is equals to minus 1 and lambda 2 is equals to plus 1. Okay, I have the eigenvalues, right? And if you can see, as I told you, one of my eigenvalue is positive, another one is negative. So if I want to find the general solution, it could be something of the kind e to the power minus 1 of t plus c2 e to the power t. Let us just not write 1 over here and take it as only this. This is going to be my general solution. So see, when my time goes to infinity, this term, though it approaches 0, right? It approaches 0 or it approaches a constant value. This approaches infinity, right? So in one direction, now these two are corresponding to the eigen directions. So in one direction, I am approaching the constant value. However, in the other direction, I am approaching infinity. So this kind of a fixed point we are calling as a saddle, right? Which has essentially some part of stability and some part of instability, sorry. Yeah. So now we will try to plot the phase plot. It's very interesting. So first we will find the vectors, eigenvector. I hope you people know how to find the eigenvector. So since we know A minus lambda I into x is equals to 0. So now since we have lambda, we are going to put that in equation and then we can assume the eigenvector as v1 and v2 and then we can find the eigenvectors. So I'm writing it directly. The first eigenvector is nothing but 1, 1 and the other one is 1 minus 1. Yeah. So these are my two eigenvectors. Now see, if I want to plot these eigenvectors, can I do it? Definitely I can do it. This is my x, this is my x dot. Remember, I converted my second order differential equation into two first order differential equations, which had two generalized coordinates, x and x dot, and hence I will be plotting x and x dot. And this is essentially nothing but the phase plot of the system, correct? This is only the phase plot now. So this is the phase plot of the system. Now, first I will plot the eigenvectors. One is 1, 1, which means a line like this. Another one is 1 minus 1, which is a line like this. Now these are my eigenvectors. Now I will see. For the first eigenvector, so if you will see, this this 1 1 you are going to get for, yeah, this you are going to get for lambda is equals to 1, and this you are going to get for lambda is equals to minus 1. Okay. So here, if I have to plot, like if I have to specify the arrows, so this one is corresponding to lambda is equals to 1. Lambda is equals to 1 is what? It is the unstable direction. So the arrow is going to point outwards. While this is for lambda is equals to minus 1, and hence the arrows are going to point inward. The arrows are going to point inwards, right? Now, you see that this point here, if I approach from this direction, if I'm going to approach, it is going to reach the fixed point. But if I'm going to come from this direction, it is going to diverge to infinity. So now if I want to plot the phase plot, what will I do? I will maybe start from this position, let us say. From infinity I'm starting. So it will follow this path. But as soon as it reaches the fixed point, sorry, as soon as it reaches the fixed point, the effect of the other eigen direction is going to come into effect and take it to the infinity. So I was approaching from this side, from here, but it took my system here. The effect of the second eigen direction, okay, it took the system to infinity. However, initially this eigen direction was taking my system to the fixed point. Similar is going to happen here also, like somewhat like this. It is going to go. Okay, I hope this is clear. And this is nothing but the phase plot, and saddle point is there. So we know what is the phase plot, and we know that the point is saddle. I hope this is clear. This was a very important concept, but essentially this comes from the concept of linear equations and the concept of eigenvalues and eigenvectors. Okay, so eigenvalues and eigenvectors actually play a very important role in case of dynamics, as you can see. Now coming on to question number 5, where we consider a Duffing equation. Okay, and now we have to talk about how does the value E E affect the stability of the fixed points, right? So this is essentially a Duffing equation. Till now what I have done is I have considered my system, and I applied the concept of eigenvalue, eigenvector, but that was a linear system. But this Duffing equation is a nonlinear system. Firstly, how will I write it in the form of matrix form? Because in the matrix form, the matrix A, which was essentially a kind of a transformation matrix, it was just having the constant values, right? It was having the constant values, or even if not that, it was having the parameters, right? It was not having the this my coordinate, right? It was not having my generalized coordinate. But in this case, if I try to write it in the form of matrix, uh, my x cube term, even if I separate a single x, the remaining is the x square, right? Which is the square of the generalized coordinate. So how am I going to work with it? Okay, so then there comes a beautiful concept of the Jacobian matrix. So what is important to understand is that for a nonlinear system, there is not any specific kind of a theorem or phenomena which tells about the stability of a fixed point. Alright. So what do? We essentially linearize the system about a fixed point, and then we assume that a small perturbation is given from that particular fixed point, and the behavior of that perturbation is used to judge the stability of the fixed point, right? So Jacobian actually gives us the linearized form of the equation, right? So see, Jacobian we have to find, through which what are we doing? We are actually working on a small domain of the system. So what that essentially happens is that, we have all studied about this example, that if we have a circle and if we consider a very small part of this circle, this is essentially nothing but a straight line. So similarly for the nonlinear behavior, if I try to take a very, for this behavior, if I consider a very small part over here, right? What is it going to be? It is nothing but a linear kind of a behavior, right? So what do? We find the Jacobian of the system, right? So what is the Jacobian? So if I have a two-dimensional system of the form f1 and y dot is equals to f2, right? My Jacobian can be written as nothing but partial differential of f1 with respect to x, partial differentiation of f1 with respect to y, partial differentiation of f2 with respect to x, partial differentiation of f2 with respect to y. You can also apply the Taylor series expansion. You can also apply the Taylor series expansion. It is going to give you the same thing. Okay, but Jacobian is essentially the matrix form. And okay, so we know the Jacobian. We find the eigenvalues of the Jacobian matrix. We find the eigenvalues of the Jacobian matrix, and we can conclude about the stability of the system. Right? So again, we have a second order differential equation. We will convert it into two first order differential equations. So we'll have z1 of dot. Why am I writing it like this? We'll just write it like this. Okay. I hope this is clear. Now what will we do? We'll find the Jacobian matrix. 0, 1. Then we will have with respect to x minus 1 minus 3x square minus e. Okay. This is going to be nothing but the Jacobian matrix. We differentiate it with respect to what? With respect to the x and x dots. I hope this was clear that this was f1, this was f2, x was x only, and y was nothing but x dot. Okay. Now replacing we will be replacing the coordinates with fixed points. So what is my fixed point? Nothing but 0, 0. So my Jacobian matrix will become 0, 1, minus 1, minus e. Simple. Now we have to find the eigenvalues, for which we have what do we have to do? We have to find out j minus lambda I. Determinant should be equal to 0. Okay, this is going to be the equation. So my lambda is going to be what? Minus b plus minus under root of e square minus 4 divided by 2. This is going to be my both eigenvalues, lambda 1 and lambda 2. Now you see, for the values of E, I'm going to have different kind of a stability of my fixed points, right? First is when my, like it would depend upon the value of E, right? So if my E, okay, let us write it in this way. We have E square minus 4. Now if my E square minus 4 is greater than 0, lambda 1 and lambda 2 are going to be what? Real, right? It is going to be here. E square minus 4, if it is greater than 0, my lambda 1 and lambda 2 are going to be nothing but real, right? Now, if it is going to be real, which is fine, there could probably be two values of lambda 1 and lambda 2. It could be positive, right? It could be negative. Yeah, it would depend upon the value of E. So if my E is positive, right? If my E is positive, what could be the probable values of lambda 1 and lambda 2, right? Both could be positive, both could be negative, one could be positive, one could be negative, right? So in that way, I could have a stable or unstable solution, right? What if my e square minus 4 is less than 0? Then lambda 1 and lambda 2 are going to be nothing but imaginary, correct? Lambda 1 and lambda 2 are going to be nothing but imaginary, yeah? So, okay, that is also fine. It could be imaginary, that's a possibility, right? So, if my e square minus 4 is greater than 0, I have my e square greater than 4 or e greater than 2 and less than minus 2, right? So if my e is greater than 2, let us suppose it is greater than 2, maybe 4. So we could have a positive or negative values of lambda 1 and lambda 2, right? Essentially, if my lambda 1 and lambda 2 are both positive, my system is what? Unstable, right? My fixed point is going to be unstable. However, if my lambda 1 and lambda 2 are negative, my system could be stable, right? But you know, there is a very interesting thing that if x cube would not have been there, if x cube would not have been there, right? My E value would directly affect the stability of the system, right? Because it acts as a damping value, right? So if the damping value would have been positive, it could have made my system come to the fixed point. If the damping value would have been negative, it would make even a small perturbation, the value would increase, right? But in case of the presence of x cube, you know, it is actually making my system a hardening kind of a system. You remember? Hardening spring, this kind of a behavior. Okay. So essentially here my x cube is also, supporting, or I would say it is actually trying to stop the system from going towards the infinity, right? However, since I am looking only at the linearized system, right? So that is why that effect could not be seen over here, right? Because this x cube effect, I've already linearized. If you see the Jacobian here, is there any effect that could be seen of the x cube? There's no effect because we have already taken x as 0. The fixed point is 0 now. So it is the Jacobian is nothing but the same, right? So, okay, yeah. So essentially, this is the thing. This is how the E is going to affect the system. You can probably take out how this is going to happen. We have already done the plot of trace and the determinant. Since we are running out of time, it is already 7:40 and I have 4 more questions to do. So I hope this could be done by you all, right? This is a very simple case and you could do it likewise. See, it's a very simple way. Like, for example, if my e square minus 4 is less than 0, what is going to happen? It is going to have an imaginary value. And if my e is positive, if it is having a positive value, what is going to happen? It is going to have a stable spiral. If it has a negative value, it is going to be an unstable spiral, right? That comes by virtue also that if it's a negative value, it will go outside. If it's a positive value, it will come back inside. Okay, I hope this is understandable. What I'm trying to say is that for this, if E is positive, spiral out, spiral in, right? I hope this is clear. And if this is for this case, when E square minus 4 is less than 0, and when my E square is actually, yeah, when my E square is greater than 4, what is going to happen? The values are going to be nothing but real. Yeah, it is going to be a real value. And if you see that whatever happens, whatever the value it is, we have e plus minus under root of e square minus 4. So we have square of e minus something and then under root of it. So it is definitely going to be always less than the value of e. Okay. So if my e is negative, if my E is negative, what is going to happen? Both the eigenvalues are coming out to be negative. Both the eigenvalues are negative. My system is going to have a stable fixed point and the convergence is going to be exponential. Convergence is going to be exponential. Why? Because both the roots are stable. If my E is positive, if my E is positive, okay, what I said earlier was if my E is negative. So, no, sorry. If my E is negative, it is going to diverge, exponentially diverge. If my E is going to be positive, it is going to exponentially converge, right? Yeah, it is going to exponentially converge. Okay, maybe I should write it. We have minus e plus minus under root of e square minus 4 by 2. We have something which is definitely less than e. So if e is positive, we have exponential divergence. Again, I'm writing the wrong thing. Exponential convergence. E is negative. Then we have exponential divergence, which is also clear from the values of the eigenvalues. Okay. So, okay, let us come to question number 6. The system given by equation is asymptotically stable. Okay. So, if you remember the Lyapunov stability, which was taught in the lecture, the first method of Lyapunov stability, which says what? Which says that if all the real part of the eigenvalues, whatever be the eigenvalues, if all the real part of the eigenvalues are negative, then we say that my system is asymptotically stable. If all the real parts of lambda is negative, all real parts of lambda is negative, and the system is asymptotically stable. Okay, so what will we do for the system? We will try to find out the first. Okay, all the real parts is negative. This is for the Jacobian matrix. Remember, this is for the Jacobian matrix. If all the real parts of the eigenvalues of the Jacobian matrix is negative, we say that the system is asymptotically stable. So we'll just apply it. We'll first find the Jacobian, which is nothing but 1, 1, minus 1, r. So we find j minus lambda I. So we have r minus lambda minus r lambda plus lambda square plus 1 is equals to 0. We have lambda square minus r plus 1, r plus 1 is equals to 0. Okay, that is how it is. Now we try to find out the eigenvalues, which is nothing but r plus 1 plus minus under root of r plus 1 square minus 4 times of r plus 1 divided by 2. We will not be concerned about whatever is inside the under root, because we are only concerned about the real parts of the lambda, right? So real parts, which is nothing but r plus 1, right? It should be less than what? 0. So r should be less than minus 1. D option is correct. Okay, coming on to question number 7. So we have equation of motion, and we have to tell which of the following options are actually correct for it, right? So for the equation of motion, this is essentially a sort of a Duffing equation, right? So let us just read the sentences and see whether it is correct or not. So first, the equation is a damped Duffing oscillator for free vibration. No, this is not the correct option because this is not damped. However, it is a Duffing oscillator for free vibration, but this is not a damped system. As you can see, there is no terms which is related to the x dot, right? Second, any disturbance will take the system to infinity. Well, this is a very non-clear kind of a statement, you know. Do you know why? Because it is written that any kind of a disturbance, right? Now, if the disturbance is very less, or should I say if it is less than 1, what is going to happen? X is going to have a significant effect. However, x cube is going to have a insignificant effect. Why? Because for example, if I say it is 0.01, its cube, it is not going to have a significant effect. So it is going to have a free oscillation. The system is going to show free oscillation. However, if my x is greater than 1, let us say 2, in that case, yes, my system could go to infinity. Yeah, if my x is greater than 1, it has a very significant value, then the system can go to infinity. It is definitely going to go to infinity now, because we have a softening kind of a system, softening kind of a Duffing oscillator. It will get softened as the value of x increases, right? But this statement we cannot say is true because it is written any disturbance, right? There should be a specification about what kind of a disturbance, whether it is less than 1 or whether it is greater than 1. Because for less than 1, very, very less than 1, it is going to have a stable solution. But for very much greater than 1, definitely it is going to go to infinity. So this is incorrect. The system is having the hardening effect. The system is having the hardening effect. No. Actually, here it should be softening. Okay, here it should be softening, and this should be the correct answer then. Okay, please keep in mind here it should be softening. I will change it when I will upload the slides tomorrow. Yeah, so this would be correct if it is softening. Okay, mind it, this will be correct only if it's written softening. For hardening, this is not true. And coming on to the last option, the linearized natural frequency of the system is 0.1. This is incorrect because the linearized natural frequency of the system is 1, not 0.1. Okay. Coming on to question number 8. So we have the equation of a Duffing, or like we have a Duffing equation, and we have this relation, right? And we have to tell whether which of these statements are correct. They are true, right? So as you can see, the values are already given. So this is just putting the values in the formula and solving, right? So we have omega is equals to, okay, so there is some change because of transfer of the PPT, different version of the software. So the under root is just for alpha 1, okay? It is not for the whole term. The under root is just for alpha 1. Okay, this should be the proper equation, right? So alpha 1, it is already 4. So what we can do is for A, we can write omega as 2 into 1 plus alpha 3 is nothing but K2, which is 1 over here. So 9 into 1 into alpha 1, which is 4, minus 10 into alpha 2 square, which is K1, 1, divided by 24 into alpha 1 square. Okay, 4 into 4. And this will be equal to, sorry, multiplied further with epsilon square. There should be alpha square over here and not a square maybe. Let me just recheck. No, no, it's fine. It will be a square only. Yeah. Okay. So coming on to, yeah, what are we supposed to do? So see over here, what is important to see is that we don't know the value of A, right? But we have to tell about the relation of omega and omega n. And you know 2, which is, like we know omega n is nothing but under root of alpha 1, which is nothing but 2, right? So we have a multiplication over here. So if the multiplication is something which is greater than 1, definitely omega is going to be greater than omega n. And if it is less than 1, then omega is going to be less than omega n. How is it possible that we can evaluate it? So see, if this value turns out to be positive, right, because we have 1 plus something. So if this value only turns out to be positive, we are going to have what? Omega greater than omega n. And if this only values turns out to be negative, then our omega will be less than omega n. So for the first case, we can see it very clearly that my omega is definitely going to be greater than omega n. So option A is correct. Coming on to option B. K1 is 0, K2 is equals to 1, then omega is greater than omega n. So we'll just put omega is equals to 2, 1 plus we have 9 into alpha 3 which is nothing but k2 1 into alpha 1, which is nothing but 4 minus 10 into alpha 2 square. Alpha 2 is nothing but k1 0 24 4 into, anyways we can see it is positive, so omega definitely is greater than omega n, so this option is also correct. We'll add another slide. We will go to option C, where we will be having 2 1 plus, we have k1 as 1 and k2 as 0. Okay, as you can see, we are going to definitely have a negative value. You know why? Because this first term is going to be positive, sorry, 0. So we are going to have 2 something in minus. So definitely it will be less than omega n. So this option is also correct. Coming on to option D, where we have k1 is equals to 2 and k2 is equals to 1. Then what is going to happen? So we have 2 into 1 plus 9 into alpha 3 k2, which is 1 into 4 minus 10 into 2 square divided by 24 into 4 into 4. So if you see this, we have 36 and we have 40. Okay, so this is nothing but comes with a negative. So, okay, this option is also correct. Okay, I hope this is clear. Now we will come on to question number 9. Yeah, so for the given amplitude frequency plot, which of the following is correct? The increase of frequency will lead to jump up from alpha is equals to 1 and jump down for. Okay, so for in order to attempt this question, first we need to understand what is this jump up and jump down phenomena, right? So essentially for a nonlinear system, what happens is that we have actually done this also, I guess, analytically. Yes, we have actually found out the relation between amplitude and frequency, if you remember. And there we got to know that my amplitude actually value depends on the frequency, and corresponding to a frequency, I can have multiple values of amplitude, right? I can actually have multiple values of amplitude. So if I can have multiple values of amplitude, then which amplitude my system is going to attain? Yeah, like for example, if corresponding to a particular value of omega, I have 3 values of amplitude possible. Then my system is going to attain which amplitude? It could attain any of the 3 amplitudes, right? But there should be a condition now by which I can know that how is it possible. So it was shown that uh, the amplitude that is attained by the system actually depends on how we are actually sweeping the frequency. For example, if I have amplitude, I have frequency, and I have the behavior of something of this sort, right? If I try to plot this like this, so you see that for this value of range of omega, I have 3 different values of, if I take a straight line, I have 3 different values of amplitude corresponding to a omega. Let us say this is some omega dash, right? So which value my system is going to attain, right? So for example, if this is 0, right, and now I start increasing my frequency, right? So what is going to happen is that my system is going to attain this path, with increasing frequency, it will increase its amplitude. Till what point? Well, till the point it does not have a continuity further. Now from here, it is not going to go towards this, it will just jump down like this and then start taking this path. Okay. So when I am increasing the frequency, what is happening? My amplitude increases, and from this point, it jumped for a very insignificant, you can say very, very small value of change of omega. It actually jumped down from a higher value of amplitude to a lower value of amplitude and then started the path. Now, if I talk about what if I start from a higher value of omega and then I start decreasing the value of omega. So what essentially is going to happen is that I'm going to have this path, and as soon as it reaches this point, now it is going to jump up like this and then start following this path. Yeah. So you see that the direction, the direction in which I am sweeping my frequency actually tells whether my system is having a jump down or a jump up. Correct. And it also depends upon how, in which direction is my amplitude frequency response uh, inclined. Like here it is inclined towards the right direction. It may happen that it is inclined towards the left direction. In that case, increasing of the frequency will lead to what? In that case, increasing of the frequency will lead to the jump up, and decreasing would lead to jump down. Correct? That is what is going to happen. So now when we read what the statements are given, so the increase of frequency will lead to jump up for alpha is equals to 1. So if you see for alpha is equals to 1, what is the inclination? Inclination is towards the right side. So with the increase of frequency, if we say, what is going to happen? Jump down is going to happen. But what is written? Leads to jump up for alpha is equals to 1. So this is not true. Coming on to the second option, the increase of frequency will lead to jump down for alpha is equals to 1. Yes, this is correct. It will lead to the jump down, and jump up for alpha is equals to 1. Yes, definitely. Because you see, it is going to follow this path. As soon as it reaches this point, it is going to jump up like this. And then it will what? Start following this path. So a jump up is happening for alpha is equals to -1. So this option is essentially correct. Coming on to option C, the increase of frequency will lead to jump up for alpha is equals to -2. Well, this is true, definitely, because now, like for alpha is equals to -1, the inclination is since towards the left hand side. So for alpha is equals to -2 also, it is towards the left hand side. So the jump up is going to be common for both of them, right? So the increase of frequency will lead to jump up for alpha is equals to -2 is correct, and jump down for alpha is equals to 2. Yes, this option is also correct. Exactly, because see, the inclination is towards the right hand side. So definitely it is going to lead to what? Jump down. Yeah, it is going to lead to jump down, and for alpha is equals to -2, it is going to lead to jump up. And the plot will be the same for alpha is equals to 0. Well, this is not correct. How is the plot same? The plot is straight, although this is, this is the resonance condition. This is what we call the resonance condition. This is what happens at the resonance value. At the natural frequency, the system actually starts oscillating at a very high value of amplitude, right? The value of amplitude increases abruptly, right? And as soon as you increase the value of frequency from that place, again the amplitude will come down, right? There is nothing like a jump up or jump down, right? There is a sudden jump and sudden decrement. This is for the case of a resonance, and this happens in case of a linear system. However, as soon as nonlinearity is introduced in the system, this resonance curve either bends towards the right hand side or towards the left hand side, depending upon the specific characteristics of the system, right? And this bending leads to the jump up and jump down phenomena. However, there could be a question that what if I try and oscillate it directly at omega dash? Like I don't do sweeping of the frequency. Then there are three probable amplitudes at which the system can oscillate. Then what is going to be the amplitude that the system is going to show? So, it would actually depend upon the initial condition and the parameter values, right? If your initial condition is near to this amplitude value, sorry, let us call it as 1. If my initial condition is near to this amplitude value 1, there are high chances that it is going to oscillate with this value of amplitude only. However, if my initial condition is near to this, it is going to oscillate at this. This is an unstable branch. This is essentially a unstable branch. So it is very less likely that the system is going to have an oscillation of this amplitude. Yeah, because it's an unstable branch. However, if you try to manipulate the system in such a way that exactly this value of amplitude, the initial condition is given in such a way that exactly this value of amplitude is possible, then yes, it may oscillate at that value. But even a very, very small perturbation, it is going to take the system either to the upper value 2 or the lower value 1. This is a very unrealistic case, right? However, it is like for an unstable system, if my initial condition is this point only, then it is always going to, till t is equals to infinity, is always going to remain at that position, right? But since it's a oscillating system, it is very difficult to say that it will be able to oscillate. However, it is possible, and you can try it numerically also. If you consider a random system, maybe a Duffing oscillator, and you try to give it this oscillation, that is probably possible numerically, but physically it is very difficult to attain. Okay, so it is very important that you learn about this jump phenomena, because there could be a catastrophic failure of the system. You see over here, the amplitude actually jumped up, right? Here the amplitude jumped down. So it may happen that the system attains such a velocity while this jump down that it may cause catastrophic failure of the system. Here there is a sudden jump of the amplitude. What if the damping is not able to control it? Then it may lead to the catastrophic failure. Okay. So yeah, this was the last question, and this was it for this week's live session. I hope that these questions were helpful for you for solving the assignment problem. And yeah, the questions are made on that basis only, that it would be helpful for you to solve the assignment problem. And if you have any doubt, you can ask, or you can keep the doubt, and then we can discuss it in the next week's live session also. Okay, so I'll just end the meeting now, and I hope you people have a great week. Okay, thank you so much.